So, hello YouTube, and I hope all of you are enjoying your new year. Sorry, this is the first video for this new year. I haven't posted anything in the month of Jan, so sorry for that. I was a little bit busy, but anyhow, so with the hope that you are enjoying your new year and everyone is happy, let's start. So this video will comprise of two topics, very short topics: formal charge and effective atomic number. Both these topics are discussed all over the internet, but I have seen and found that most videos comprise of 10 or 11 minutes on each topic. I am assuring you that this video will comprise each one within 4 to 5 minutes, and I hope that this will help you to understand the topics better and solve it in your examinations also in a better way, because this is the way I have learned it, and believe me, I have done it quite well. Anyhow, both the topics are present in solid state chemistry and we'll discuss it. So probably you are seeing the definition right now of formal charge. It's some kind of nerd definition, but we have to remember it because we have to get the marks. Anyhow, the definition says a formal charge is a theoretical charge assigned to an atom or molecule, assuming that the electron in all bond are shared equally. Very nerdish definition. What is a general layman terms idea about this definition? The definition says that formal charge is a theoretical concept which is used in solid state chemistry to understand what the initial charges was there over a particular atom or a molecule, and after forming a bond, what is the new charge. Now the question is, if this is a theoretical concept, why do we need this? Well, this concept is used in a very good way. The way is that if you know the shape of a molecule, for example, we know that a carbon is an sp2 hybridized carbon in a given molecule. It can be any molecule, and we know that the particular formal charge of that carbon is 0. Then if I happen to see another carbon which is also sp2 hybridized and have same formal charge, I can say that both of them will have same oxidation number without calculating any oxidation number for either of them. There are many other use of formal charge. If you want them, just mention them in the comment section below and I will discuss it. Anyhow, let's move to the formula. Here is the formula. F equal to V minus N minus B by 2. What are those things? F is the formal charge, V is the total number of valence shell electron, N is the total number of non-bonding electron, B is the total number of shared electron. That's it. You can pause the video right here. I am posting a example section, but before going to the example section, pause the video and see if you haven't understand anything else. Just go back, review the video, and then we'll continue. So let's move to the example. We are going to find the formal charge of carbon in carbon dioxide. Let's move on. Here is the formula. F is equal to V, total number of valence shell electron of carbon, which is equal to 4. Total number of non-bonding electrons in carbon dioxide is 0. How you will find out? See, here is the carbon dioxide Lewis diagram. Carbon is having 4 valence shell electron shared between 6 valence shell electron of oxygen. So total number of non-bonding electron is 0. Carbon doesn't have any additional electron left. It is 0. Total number of shared electron is 8. See, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons shared by 2. It will give you 0. Okay, you have to draw the Lewis dot structure. From that, identify number of valence shell, number of non-bonded, and number of non-bonded, and number of shared electron. Let's move to another example. We are going to identify the formal charge of aluminium chloride. Same aluminium. If you see, it has the last electronic configuration of aluminium chloride. You will find that 3 electron, 1s2, 2p1, I think. Sorry, 3s2, 2p1 something. Anyhow, just aluminium has total electronic atomic number of 13. Solve it, you will find that 3 electrons are at the valence shell. I just can't remember exactly. I have to do it. Sorry, it will just longer the video time. Sorry, let's continue. So 3 is the total number of valence shell electron of aluminium. We are supposed to find this aluminium formal charge. Okay, total, again, draw the structure. You will find that there are 6 electrons shared within aluminium and 3 chlorine. So it has given us 6, and there is no non-bonded electron left for aluminium, so it is 0. divide this 6 by 2 according to formula and you get 0. There is another method, a shortcut method without using this formula. Let's discuss that one. So guys, this is a shortcut method. I know that looks like a 3, some will say that looks like a 5, and yes, that's a S. It's an optical illusion I have learned somewhere. And yeah, let's continue. The shortcut method is actually telling you that from the very term definition we can find it out. How? You have to identify the initial charge, see, initial total charge, identify the final total charge, and then just subtract them, final minus initial, you will get it. So let's have a look. Let's go to the very examples that we have solved. In carbon dioxide, just take carbon before carbon dioxide is formed. You will see carbon is in its natural form, carbon, without any charges, no plus charge, no negative charge, so it is 0. After the charge is formed, sorry, after the molecule has been developed, if you go to the Lewis dot structure, you will see still carbon doesn't have any charge. So final charge is 0, initial charge is also 0, so final minus initial will give you 0. Same thing happens here also. Aluminium is in its elemental stage with no charge. After forming, it doesn't have any charge either. So just subtract it, you will find it out. It's 0. Now before we end the video, I have a small question. You have studied this entire formal charge, I hope, and now we are around 4 or 5 minutes in the video. So just a quick question. What does formal charge number signifies? Means what happens if the formal charge is 0? What happens if formal charge is negative? Or what happens if formal charge is in positive? Pause the video, think over it, and then I will tell the answer. So I hope you have paused the video. Here is the answer. If formal charge is 0, just like in these two examples that we have solved, we can say that in the initial case as well as in the final case, the given atom doesn't gain any additional charges at all. In its elemental form, it has no charge, as well as after forming the bond, it doesn't gain any charges. It's a neutral. But if formal charge is in negative, formal charge can only be negative if both n and b minus 2, both as a together sum, exceed the total number of valence shell electrons. That is only possible if the given atom takes additional electron. That means if a minus charge is been added here, additional electrons are present, then value of F will be negative. Formal charge is in negative. That signifies that the given electron considerably have more number of electron than it has in its initial elemental stage. What happens if formal charge is positive? If formal charge is positive, that means the given considerable atom has lost electron. A positive charge has been developed. That's the interpretation of the three values of 0, a positive and a negative of formal charge. Generally, most cases, if the compound is been formed, we generally say it's a 0. We generally find it is 0 until and unless it is specified that is an ion or a Zwitter ion maybe. Zwitter ion case can be found in case of ozone. That's an homework for you can consider. Well, I am not your teacher. I am the same age as you. So it's not a homework, but just do the formal charge of ozone and you will find out what I'm talking. It's a Zwitter ion. It considers both plus and negative charges in it. Solve it, and if you face any problem, just mention that in the comment section. I will try to solve it. And if you like the video, click the like button. If you dislike the video, click the dislike button, and please mention why you dislike it. And I hope you subscribe it. I'm trying my best to upload new content as much as possible. So see you next time. Bye.